In this video, we'll discuss the logic of the ANOVA test and a little bit more about that experiment-wise error. So again, the question in the last video is why use an ANOVA if a t-test can compare two means? So again, a t-test, we get a type 1 error for each t-test, and that's alpha. That type 1 error is that false positive. So when the null hypothesis really was true, but you reject that null hypothesis. So if we have three groups, we get test 1 comparing treatment 1 versus treatment 2, we get an alpha 1. Test 2, we compare treatment 2 to treatment 3, we get a second alpha. And if we compare then treatment 1 to treatment 3, because again we have one factor with three different levels, 1, 2, and 3, we need to compare each of those to each other. Our experiment-wise alpha ends up being alpha 1 plus alpha 2 plus alpha 3. So we have the same type 1 error for each test, but across the experiment, we have this combined effect. In an ANOVA, it evaluates all the mean differences simultaneously with one test. So one test compares all three means. We have one type 1 error rate. So test-wise alpha equals experiment-wise alpha. So this is the test-wise alpha, and because we only have one, it doesn't change. So that's what experiment-wise means across the experiment, and test-wise means across the test. So the ANOVA avoids the problem of the inflated experiment-wise alpha. All right, let's compare the t-statistic to the F ratio. Now when we're talking about the t-statistic, whether it's one sample, independent measures, or repeated measures, we're looking at mean differences. We had two different groups, two different conditions, sample and a population, and we were looking at the differences there. And it's easy to look at differences when you only have two groups for a mean difference. And our formula looks something like this. Some sort of mean difference on the top and estimated standard error at the bottom. A little variation for each of the different types of tests we discussed. Now, because it's difficult to know how to compare two or more means, in an F ratio, we use variance. So we're using the sample variance to know if there's a difference that's due to chance, random error, or due to the treatment effect. And this is what our F ratio looks like, the variance or differences between sample means, and the variance or differences expected with no treatment effect. We'll see in a few minutes that this variance between sample means is comparing how much variance there is between the means in that experiment, which can be due to random error and treatment effect. And then here in the denominator, we're looking at the differences within each group that will tell us how much variation we have in the population. And again, that variation within the population that's due to random error or chance without any treatment effect. So for our between treatments variance, we're looking at the variability that results from the treatment conditions. Okay, here's one treatment, here's another treatment, and here's a third treatment. It measures the differences among the sample means. How much difference is there between the mean of treatment 1, treatment 2, and treatment 3? Within treatment variance is looking at the variability within each sample. So how much variability do we have in sample 1? How much variability do we have in sample 2? And how much variability do we have in sample 3? We know that individual scores aren't the same within each sample, so we want to know within that treatment, how much variation do we have? So here again, the between treatments variance is looking at the variance between the sample means, and the within treatment variance is looking at the variability within each sample. So our F ratio then is the differences including any treatment effects over differences with no treatment effects. So looking at this F ratio, total variability can be broken down into that between treatments variance, where we have systematic treatment effects that's caused by our manipulation, and then we have random unsystematic factors. variance that just happens due to chance or error. That's the numerator of our F ratio. Then we have the within treatments variance, which is random, unsystematic factors. So variation that happens that's not due to any treatment. So if you compare these here, these are the same. The difference is this. So we are looking to see if the numerator compared to the denominator, if we get a value that's much bigger than 1, the bigger that value is, the more chance we have of having significant results. So again, this is the denominator, just random error within the treatments, just due to chance, due to individual differences, whatever. And then here we have the same variance, but we add systematic treatment effects. And the denominator of the ratio is called the error term.